Good afternoon, everyone. So we're going to continue talking about our neural networks today. We're going to focus more on the training side, but let's just think more about, review what we did last time. So we basically proposed this structure that has two stages. Each stage has a linear transform followed by a simple nonlinearity. We can recognize the second stage as just a linear classifier with these features. And the first stage then we can interpret as a way to take these raw features and transform them to some other features that work better for linear classification, which means that these features here are approximately linearly separable. And of course, everything is trained from the data. We have to learn these parameters, and we do this with maximum likelihood, given a training data set, just like always. So today we're going to talk a little bit more about how we compute the gradients through backpropagation, and we will talk a little bit about making the algorithm itself a little bit faster through something called stochastic gradient descent. Okay. Were there any questions about anything from last time? Everybody good with the main idea? Okay. So let's think about gradient descent algorithm. We learned about this back in Unit 6. So what we want to do is we want to find the minimizer of some cost. If this is the maximum likelihood parameter, then this cost would be the negative log likelihood. And when we have a model that has independent training samples, the log likelihood gives us a sum. And so the difference between this j here, that's the script j, this is over the whole training set, whereas this little non-script j is only for the ith training sample. Something that's just a little bit different than what we did before is now we have a 1 over n in front, which is just basically signifying an average over the training samples rather than just a sum. But we can think about this as just a definition if we want. And so what we do with this, how we minimize this in practice is we run the gradient descent algorithm. So at the kth iteration, it looks like this. Our new parameters for iteration k plus 1 are the parameters iteration k minus a small number times the gradient of our loss. And we know that as long as this number is small enough, at least if this is a convex loss, then we should eventually converge to the minimum. Or if not, then we should converge to at least a local minimum. So for these neural networks, unfortunately, we don't have convex losses, and so we just hope that we eventually converge to a good spot. And through clever algorithm design, clever initialization, this does tend to happen in practice, and the evidence is just all the great performance that people get out of these deep networks. Okay, so this is our gradient descent algorithm, and I'll highlight that. So if we plug in the expression here, or we take the gradient of this expression, then the gradient can go through the multiplication and the sum, and we get this. And as you can see, for every iteration of our algorithm, this says that we have to compute n scalar gradients and sum them to get it. Okay. So the problem with this is that once we move to these neural networks, we need, generally speaking, large data sets for them to work well. And once we move to deep networks, very large data sets. And so just as an example, a famous data set we'll talk about later, it's called the ImageNet dataset. That has 14 million images in it. And that's not even the biggest data set that people use now. So basically, we have to worry about computation. We worry about, for every single gradient descent step, and there may be hundreds of thousands of these steps we need to take. This says we need to sum over millions of samples. That's an issue. We don't want to do that if we don't have to. So that's where we want to see if there's a better way. Any questions so far? Okay, so what we're going to do is, instead of taking all the samples of the training data set and using them all at every iteration, we're just going to take a random subset of B samples. And we'll show that that actually works fine. So that is known as stochastic gradient descent, using these things called mini batches. Okay, so as shown on the picture on the right, if this is our total data set, so each row in here would be one sample in our data set, a mini batch is just going to be like pulling out a relatively small subset of samples. Mini batch sizes might be like on the order of 100 or something like that. Versus, like an MNIST, there were 50,000 samples total. ImageNet has 14 million, and so on. So we're talking about something more like on the order of 100. And we're just going to use one mini batch for one gradient descent update. So that's the idea. So here's sort of just to spell it all out. At step T of our algorithm, and we're going to have now let's say a total of capital T steps, but at step little t, we're going to randomly select some subset of indices. So if the numbers 1 through n give us the indices of our full training data set, we're going to call I sub t some subset of that has, let's say roughly 100 samples. Then, rather than using all n of them here and dividing by n in that average, we are going to use just the samples from our subset. And this absolute value of a subset just means the size of the subset. So here we're just doing an average over the gradients in that subset. We're going to give that a name. We're going to call it G of t. It's our approximate gradient at iteration t. And then we're just going to use that approximate gradient in gradient descent. So it's not exactly gradient descent anymore, because we're not really taking a gradient, the exact gradient, with respect to the whole loss function like we were on the previous page here. We're actually, on the next page, we'll argue that what we're doing is we're using an approximation of that gradient. And it's a random approximation. It's random because we randomly selected that index subset. So that makes this guy, you can think of this as random, and it makes our descent direction random. So that's the idea. Is this making sense? Maybe I'll draw a picture. So I'll draw it with a pen. So we've sometimes drawn things like this where we have some cost contours, and we want to start somewhere and converge to the bottom. And so gradient descent might do something like this. And then, so we're basically taking some steps like that. That would be GD. So stochastic gradient descent now is going to be taking the first step not exactly in the same direction as gradient descent. It's going to be some random variation. Maybe it's pointing that way. And then the next time, it is going to be some approximation of this. Maybe it's, again, not perfect. So maybe it's converging, or maybe it's going that step. And then maybe the next time like this, and so on. So it's going to be just sort of randomly tracking that smooth gradient descent trajectory. And when it gets to the bottom, maybe it jumps around a little bit. But that's sort of the difference between SGD and GD. Okay, it's making sense? Any questions? All right, so what we want to do is we want to convince ourselves that this is a good idea. So basically what we can say is that our gradients, G of t, are going to be correct on average. In other words, they're unbiased. So to write it in terms of an equation, you could say the expected value of gt, the gradient, given your previous location theta t. Well, okay, what is that? So remember that for the gradient, we took this random subset of indices, and we're just going to choose them uniformly at random. So, no particular index is favored over any other one. So when I draw this subset, I have equal probability of selecting all of the indices. So that means that on average, you can say with probability, 1 over n, I would have selected the first one with the probability 1 over n, the second one, and so on. And so when you look at what happens on average, you just have a probability of 1 over n for all of them. Okay, so even though this, for one realization of this trajectory, we said it's a little bit off. If you do this experiment again, maybe the next time it does something like this, and another time it does something different. And if you averaged all of those trajectories, you would get this original gradient descent one. Okay, so on average, it's doing the right thing every time, but there's variation around that average. So it's doing a little bit the wrong thing every time, but on average, correct. Okay, so that's what we mean here, is that this gradient is on average giving us exactly the gradient we want. So that's one of our justifications. Is this making sense? Okay. So now we can use that to just go a little bit further and say that on average, the new parameters, given the old parameters, are also correct. So that's pretty easy to prove. All we have to do is substitute in the equation for the new parameters, which we know is this, in stochastic gradient descent. And now notice we're conditioning on the old parameters. So that means when we take this expectation, this is like a constant. The step size, we'll just say that that's something that's, well, let's say we choose it. We'll just think about it as a deterministic. And then finally, we have the expectation of g given theta, which we said is the truth. So here you can see that on average, your updated parameters are exactly what gradient descent would give you without any approximation. Okay. But again, if you look at a specific gradient realization, g of t is not exactly equal to the true gradient. There is some little error. We'll call that epsilon t. But what we've shown up here is that error is zero mean. You can think about it as a gradient noise. Gradient noise is zero mean. So the gradient noise is what is making us, so if this is the true gradient, then this is the one realization of the gradient noise pushes that way. And maybe if this is the true one, the next realization, the gradient noise pushes that way. So the gradient noise is pushing us in these random directions, but on average, it's zero. Okay, so as a result, as like the pictures I showed, the stochastic gradient descent trajectory is more noisy than the true one. It bounces around a bit. Maybe it takes some crazy moves. So what you can do is you can just reduce the step size, take smaller steps when you have this randomness, and then taking those smaller steps will sort of average things out in a certain sense. So what you see is the smaller that you make your mini batch, the smaller you want to make your step size to compensate. Because the smaller you make your mini batch, the more random things get at every iteration. So you compensate the smaller step size. Okay, so that's basically the stochastic gradient descent algorithm. There are fancier versions of this algorithm that they do more than just take a gradient step. They might incorporate things like momentum, where you look at the previous gradient and you have a little bit of a term that says keep moving in that direction. There's all sorts of tricks that people have proposed, many different algorithms that you can choose from when you look at Python implementations of this stuff. Some work a little bit better in some circumstances than others, but okay. So now just a little bit of details and notation for how you implement this stuff. So imagine that, as always, we have n samples in our training data set. That's the number, the notation we've used all semester. And we're going to say that the number of samples in each mini batch is going to be b. And we're also going to say that the mini batches don't overlap at all. So the intersection among all the different mini batches is 0. So there, the total number of mini batches, if I can use every sample only once in one mini batch, would be t. T equals n over b mini batches total. So it's like, back to this picture, b is a number of records here, the number of samples there. N is a total number. And so the number of these mini batches that you find in the total is capital T. Okay. So we're going to do one stochastic gradient descent update per mini batch. And therefore, to get through the entire data set once, we'll take T updates. And the name people give to that number, T updates, which is basically the number of updates it takes to make your way through all your training samples once, that's called a training epoch. So an epoch is just defined as how many updates to get through your data set. And usually when training these networks, people talk not about the number of steps of training, but the number of epochs. How many times did you go through your full data? Because if you make your batch size, half as small, that means it's going to be more noisy, and you'll probably take more steps to get through it. But you'll have twice as many steps to get through your full data set size if you made your mini batch twice as small. So things kind of balance out, roughly speaking. So that's why people talk in terms of training epochs rather than number of updates when training these algorithms. Okay, so any questions so far? All right, so this is how we do it. In each epoch, what we first do is we randomly shuffle all of the n training indices. So we'll call the training indices I, like always, and we shuffle them. So maybe the first I is 1023, and the next I is 4, and the next I is whatever. So all the I's got shuffled. Once they're shuffled, we can just partition them into contiguous subsets. So we take like the first 100 shuffled indices, that will be mini batch 1. The next 100 will be mini batch 2. The next 100 will be mini batch 3. Okay, so shuffling first and then just chunking out the mini batches. And finally, we, for each subset, we use that to compute the gradient and the cost in stochastic gradient descent. When we come to the next epoch, we want to reshuffle the data. We don't want always the first mini batch to have the same samples in it. That would cause some weird stuff. Maybe the network would grow dependent on exactly that structure. We wanted to shuffle every epoch, reshuffle the data so that every time we form a mini batch, it has different samples in it. Okay, so that's how we do that. Yeah, that's really all I wanted to say about stochastic gradient descent and mini batches. And yeah, this is a little bit more intuition about why this works well is when you look at something like gradient descent, notice how in the first iteration, we're moving in this direction, which is not actually the direction we want to go in overall, right? We want to move over here. So you could say, like, if I'm going to be moving in the wrong direction for gradient descent a lot of the time, why should I work so hard to compute that direction? I shouldn't waste resources computing something that is just wrong in the first place. So that's why it's okay to just use a mini batch rather than the full data set. Because now instead of moving exactly in that direction, we're moving a little bit this way or a little bit this way. That's fine. We will get a chance to correct that later. So it says, you know, gradients themselves are not taking us in the right direction. Just compute them approximately and compute so that if I can compute them approximately, I can compute many, many more of them per unit time, and therefore I can get many, many more corrections. So that's a little bit more intuition about why we're doing this. All right, are there any questions at all about any of this mini batching stuff? Yeah.
So if you're using all n samples eventually, why don't we just use gradient descent? Maybe I didn't catch that.
Because it's very expensive. So if I have like 14 million samples and gradient descent says use them all at every iteration, right?
Okay.
That's what gradient descent says. Use all n of them. And the point is that, especially in the early iterations, the gradient is kind of pointing in the wrong direction anyway, in terms of it's not bringing you directly to where you want to go. So why are we spending so much resources to precisely compute this thing that's taking us in the wrong direction anyway? Let's just approximate it with a simple computation, and it's going to take us maybe a little bit in the wrong direction, but then we're going to correct for it in the next iteration. If I make smaller mini batches, I have many, many chances to correct. And every update step goes so much faster because rather than computing 14 million gradients here, I just compute 100. Each gradient, as we'll see, is kind of expensive, especially when you have a deep network. You have to move all the way through the network and do all these computations. And so this way, you just have to do relatively few of them per update.
So is that every year, is that every epoch that you're, like the 100 iterations, not quite catching that?
So for every training sample, you have to compute one gradient, right? And the mini batch has B samples, about 100. So that means for one gradient descent step, you have about B gradients to compute. Now that's just B of them. To make your way all the way through the training data set, you will need to use T updates. So the total number of gradients to make your way all through the data is always the same. It's always n gradients to make your way through the data set once. But in gradient descent, you only get to do one update for those n computations, whereas in stochastic gradient descent, you get to do many, many updates, many, many corrections. So, okay.
On average, does it perform better than gradient descent simple, or is it like that? If it is on average like that, so why are we doing this?
What do you mean by on average?
Just like because we are taking random steps, and if we average out all those steps, we get just on average it performs just like gradient descent.
Yeah, so every step in stochastic gradient descent is on average. But like, there's maybe different ways to think about the average. So imagine that I say, what kind of progress can I make going through my data set once? So if I'm doing gradient descent, and then I would maybe move, I'd move in this direction, and you can see I'm never going to get close to my minimum with any step size. Whereas with stochastic gradient descent, if t, the number of updates per epoch, is many, let's say it's 100 something, I have 100 little bad steps I can take, but you see that they will eventually bring me a lot closer to my minimum than that one very precise bad step with the same amount of computation. So in some sense, stochastic gradient descent is way more efficient on average. It just depends what you mean by average. Okay. In terms of like the actual step you're going to take, this gradient descent is, let's say that's a reference, and then on average, stochastic gradient descent is taking you the same way, but if you look at any realization, it's going to be a little bit off. You could even possibly go backwards. It can happen. But, on average, it's taking you in the right direction.
But can't you solve that problem by taking a smaller learning rate and gradient descent?
Yes, we do tend to take a smaller learning rate in gradient descent. And so it has the effect of sort of averaging out all our little mistakes. So that, maybe I have some in a great direction, I have some in a bad direction, but on average, I'm making them, maybe I didn't explain that well. Yeah, if I have, I guess there's several things going on. One thing is that you have many steps you can take, right? And then there are going to be noisy steps. So to remove that noise, you generally do want to reduce your step size. That's true. So you won't go as far with every step. But if you look at, let's say, I don't know how to think about it, maybe like if you're going to travel a certain distance, then, I don't know. It's hard to think about things that way. But am I answering your question? Yes, you do want to use a smaller step size with stochastic gradient descent.
If we can just use a smaller step size with gradient descent, why are we even doing this stochastic gradient descent? Would it be the same if we just take a smaller step size using normal gradient descent?
No, because with normal gradient descent, like if you take like 1 unit of computation, let's say you budget me with, I can go through all my training samples once. And now I ask, which technique is going to get me closer to the solution? So gradient descent can only take 1 step, right? Stochastic gradient descent can take many steps. So regular gradient descent, let's say we can use whatever step size we want. I can, let's say, optimize that step size. So I'm going to travel in this direction, and I kind of optimize, where I go along that line. But you can see that line is never taking me over here. With stochastic gradient descent, I can take many steps. So maybe the first time I go on average in this direction, but I make a little progress. And the second time I go on average in this direction, I make a little progress. Third time on average in this direction. And maybe I take 100 steps with that same amount of computation that gradient descent got to take 1 step in. So with all those corrections, I can get a lot closer to the goal. So that's a big difference.
But don't you run the risk of getting it wrong? Because let's say in a case where your data set you considered sort of took you in the opposite direction, would you just run the risk of going the other way around?
But remember, it takes me in the opposite direction very rarely.
But it does mean it is not as efficient, it is not as correct as gradient descent. There could be cases where it just turns down and goes the other way.
Yeah, but it's one of, let's say, 100 steps you get to take. So gradient descent gets to take 1 step, you get to take 100 steps. Maybe one of your 100 steps is in the wrong direction, but all the other ones are in a pretty good direction.
But these steps are serially taken, and you take one step and then you take next step, then you take
Exactly.
next step. So if your first step is wrong, that means you're going the other way around. Isn't that it?
It just means you went back a little bit and now you can go forward the next time. And if your step size is small and you go backward a little bit, then you're not really much worse off than when you started. So, okay. All right, good. Good discussion. Okay, so that's the algorithm. Now let's change gears a little bit and let's talk about how we compute gradients. So let's first think about what we have to do. So our parameters theta for our two-layer network are the hidden weights, hidden biases, output weights, output biases. So these are all the things we have to learn. And we said we're going to do our optimization through this mini batch stochastic gradient descent. So here's our step size. IT is the subset of indices we're using at the tth iteration. This is the size, so this is doing an average. And then these are the different gradients that I need to compute at for the ith sample. And because I'm using a different subset every update, this cost has a T on it. Okay, so the question now is, okay, how do we actually compute these gradients? So in particular, these are the things we need to compute. We need to compute the gradient of the cost with respect to the hidden weights. But remember, this is a whole matrix. So we have output index L and input index J. So those are the scalar components of this weight matrix. We have to compute these scalar gradients for all L and all J. Okay, then for the biases here, we have to compute these scalars dj, db, h for all the different components in here, which we can index by L. And then same thing for the output. That's a whole matrix, so we can index those by k and L, the kth row, lth column. And then this is a vector b0, so that would be a vector indexed by k. Okay, so these are all the different things we need to compute. And of course, the equations for computing all of these, they would look very similar. You're just going to be changing indices, but the equations for these might look different than the equations for these, which may look different from the equations for these, and so on. So basically, for each one, we have to do sort of a separate derivation to see exactly how we're going to compute those. And that's what we're going to do in the next few pages. But one thing just to, as you can see, there's already a lot of notation. We're going to drop the batch index T from our notation. We're just going to imagine we're at the tth update, and we're just focusing on what we're doing in that update, so we don't need to talk about T anymore. That will help clean up our notation. Okay, so in order to help us organize the computations that we need to perform, we're going to build what's called a computation graph. It's nothing more than a graph that shows how the different variables are connected to each other, how they depend on each other. So these green ones are our observed data. The blue ones are the ones that we need to train or learn. And then all the purple ones are the ones that are dependent somehow on our training and observed variables. So as you can see, if we imagine starting with some features, xi, this is a collection of features over our data set, or actually over our mini batch. That's what the brackets here mean. So we have a mini batch of features, and imagine that at this iteration, we know some weights and biases in a hidden layer. Well, remember that those two things together determine the scores for the hidden layer, and this is going to be a batch of scores. Once we know the scores, we put them through that nonlinear activation, and so those alone determine the activations. These are the hidden layer activations, or the inputs to the final layer. So if you take the inputs to the final layer and its weights and biases, those together give you the scores, the output scores, and if you know the output scores and the training labels, you can compute the cost, the negative log likelihood, right? So it just shows you how all the different parameters are connected together. Starting with the inputs to the network and ending with the loss, which you could say in some sense is the output. Okay, so this computation graph is just nothing more than something to help us organize our computations. Okay, so the first thing we have to do, remember when we start, all we know are the inputs, we know the training samples, and we know the weights. That's all we know. So the first thing we need to do is figure out all this other stuff. Once we figure out all that other stuff, then we can figure out the gradients. So we call this the forward pass. The forward pass is just figuring out all the variables themselves before we do the gradients. And the forward pass, sort of as suggested by this computation graph, you start to the left and you make your way right. So you start with these inputs and these coefficients, and from them you compute these. Then from those you compute these. Then from those and those you compute these, and then finally from those and those you compute these. Okay, so that's just how we're going to do it algorithmically. So the forward pass, to write it in equations, goes like this. We start with our xi's, and we start with our weights and biases, and we know that this is the equation that brings us the hidden layer, the vector of hidden layer scores, and we have to do this operation for every index within our training batch. So now I is just indexed from 1 through B because we have B items in our training batch. Okay, so we basically compute this equation, and then we know all these z's when we're done. Now that we know those, we can put those through our hidden activation function, and we can compute all our different activations. Once we know the hidden activations, we can put them through this linear equation here to get our output scores. And with our output scores, we can combine those with our training samples to get our loss. Okay, so now we've sort of initialized all those variables, and now we're ready to do the backward pass, which is a bit more complicated. That's what we'll talk about next. Okay. So one thing to note is, remember how we have different ways of writing the loss. So we said we can write the loss in terms of the output scores, z, or we could have an output activation function and compute outputs AO, and we could also write the loss in terms of AO. But for this derivation, we're going to take the somewhat simpler approach and just compute the loss from the final output score z. We're not going to have any activation function here. That just makes it simpler, and we don't need one, so we're just going to omit it. But if you would like to implement it that way in the code, PyTorch, which we'll discuss, allows you either option. If you have, let's say you're doing logistic regression, you can put in a sigmoid here, and you can get the AO scores output, and you can define your loss based on those scores. You just have to choose the correct function within PyTorch. You can have either option. All right. Okay, any questions so far on the computation graph? Did you have a question or no? Yeah? Okay, all right. Okay, so the forward pass, as you can see, is pretty straightforward. To talk about the backward pass, let's first review the chain rule, because understanding the chain rule is really the key to understanding the backward pass. And we're going to try to visualize the chain rule just with one of these computation graphs. So in this computation graph, you can see that z depends on y, and then y depends on x. So you could say that the dependence of z on x is through y. So as we know from basic calculus, if you want to do dz dx, you can break that up and do dz dy times dy dx. Okay, that's just the basic chain rule with, it's not the multivariable chain rule, it's just basic chain rule. These are all scalars. Okay, so you guys know that well. You've been using it for many years. Okay, now imagine that what I do is I insert another variable in this graph, u. So if I want to do dz dx, I could do that with the chain rule like this, dz times du, dz du times du dy times dy dx. So that is an option. I can break that up into a product of 3 computations, but I don't have to. If somehow I know dz dy, then I can bypass that u node. I can do dz dx is dz dy dy dx. So I don't have to involve this if I don't want to, right? Because here you can see that this product, based on this, is just dz dy. Okay, so I could just use that and that to compute my chain rule. I don't have to use u. So we have choices when we do chain rule. Okay, so now let's talk about the multivariable chain rule. So the multivariable chain rule occurs when you have multiple paths in the graph. So that's essentially what's happening over here. So here this is saying I have a bunch of variables yi that are between x and u. Although the graph is not explicitly notating it, maybe just for clarity, we could notate it. So it's sort of like, imagine there's a bunch of these nodes here, and the data is really going in parallel through them. This is like the first, y1, y2, y3. So you can see how the data to get from x to u, it actually flows through different yi's. And this means we can't just ignore 2 of the yi's and use the third. We actually have to use them all. And that's what the multivariable chain rule tells us to do. It says basically compute these partials like, so I guess, okay, the way that I wrote it in this equation, I thought about the dependence directly to there. But it basically says sum over those branches. So this gives you one chain rule thing, and then you add that to this other one and add that to the other one. Okay, so that's the multivariable chain rule. And it's really going to be important when we see the computation graphs to recognize when we use the multivariable and when we don't. You have to look carefully and ask yourself, is this happening or not? If that's not happening, you use the single variable chain rule. But if there is multiple paths, then you have to use the multivariable one. Okay, so as we'll see, sometimes it might be a little bit tricky. You have to look very closely to see what's happening. All right, are there any questions on any of this stuff? Chain rule? Everybody good? Okay. So we're gonna basically do the backpropagation derivation 3 times with increasing difficulty and sophistication. We're going to start with the simplest possible case, which is where all the variables are scalars, so no vectors and matrices, and we just have a batch size of 1. Okay. In that case, the computation graph that I showed earlier can be written like this. So we have a scalar feature x, we have a scalar weight and bias, WH and BH, and this is the equation that tells us how the scalar score, ZH, is computed. We just simply scale x and shift it with BH. Okay. Once you have that single scalar hidden score, you put that through your activation to get or put that through your activation function to get your activation AH, and that's again a scalar. Once you have that, you scale it by W0 and add B0 to get Z0, and then finally you take these 2 scalars and you put them in this loss J to get your script J. Okay, so that's the simplest possible case. Let's see what happens in this case, and then once we've mastered this case, we'll add some complexity. Okay, so what we're going to do is we first do the forward pass. The forward pass is that set of equations, because when we start, all we know is we know x, y, and we assume we know these weights from the previous iteration, or if this is the first iteration, we somehow initialize them. So that's what we know. So the very first thing we need to do is we need to figure out all this other stuff. And that's what we do with our forward pass down here. Okay, so we just execute those equations, and once we've executed them, that means we know all of those quantities. Okay, now I want to figure out the gradients. My eventual goal is to do dj dwh, dj dbh, dj dwo, and dj dbo. And you can see that in order to do that, we have to think about the computation graph that connects those variables. Okay, so what we're going to do is we're going to start on the right side. Forward pass took us here, and we're going to move left. So we're going to start here and move left. So the first thing that we're going to compute, which is sort of a building block to help later computations, is dj dzo. Okay, so dj dzo, to figure out what that is, we have to look for the equation that relates the script j to zo, and we see it involves this small j. So then d big J dzo is just d small j dzo, right? Or we can maybe write that as j prime zo. So that's easy. We can't really say more about it without knowing exactly the form of the small j. But you can see that one important thing is we wouldn't be able to compute this if we didn't know zo, and that is something that we computed in the forward pass. So the forward pass is giving us things that are useful for the backward pass. Okay, so the first thing we compute is this, and then we store this. This is now just going to be a number. We computed and stored that number. Next thing I want to do is dj dah. So with the chain rule, we know that that's dj dzo times dzo dah. So that's what this equation says. Now, this first term, we know exactly what that is because we already computed it and we stored it. So this is just a number. So the only thing left to do is figure out what is this number. So that's dzo dah. So we have to find the equation, linking them. And then you can see simple calculus dzo dah is just wo, right? So now I know what that number is. I multiply it by this number, and now I know that number. I store that. Now we move one further step. I want to do dj dzh, and I can do that by dj dah, dah dz, h. Right? And notice how I skipped over this. I don't need to involve that if I don't want to. And there's no sense to, because this first thing, dj dah, is something that I just computed. So I can use that, and the only thing I have to do now is dah dzh. But that is, again, relatively easy here. This is the equation that links them. So dah dzh is just going to be the derivative of my activation evaluated at zh. So I'm going to call that little h prime at zh. So now I compute this, and I multiply that by this number that I know, and now I know this number. And now that I have all these gradients with respect to my purple nodes, I'm ready to actually get the gradients with respect to the parameters. So the first thing, I'm going to take the closest one to the output, which is bo. So I want to do dj dbo. But as you can see with the chain rule, I can break that into dj dzo times dzo dbo. That's what we've written here. Now the nice thing is dj dzo is something that I've computed and stored. So that's just a number. I know what that is. So all I have to figure out now is dzo dbo. So I just have to go to this equation, and I see dzo dbo is just 1. Okay, great. So that means I can multiply 1 by this number to get dj dbo, and I have that term, and I can use that in my gradient descent step when I'm ready to do so. My next task is dj dwo. But as you can see, the computation graph is sort of the same. It's dj dzo times dzo dwo. And once again, dj dzo is something that I have computed, so I'm just going to reuse it here. The only thing I have to do new is dzo dwo. So for that, I look at the equation, linking zo and wo, and I can see that dzo dwo is just ah. Great. So I know that because I computed that during the forward pass. So I have this number multiplying this number gives me this number, which I now have computed and stored, and I'm ready to use it whenever I do gradient descent, or stochastic gradient descent. So now we're getting closer to the end. Finally, I want to do dj dbh. Although I have a deep chain of dependencies, I can skip what I don't want to involve, so I can do dj dzh times dzh dbh, like this. And now this dj dzh is something that I already computed, so I'm done with that. And I just have to do dzh dbh. I look at this equation and I see, oh, dzh dbh is just 1. So that's done. I multiply this times 1, and I get this term. And I only have one more to compute, dj dwh. So I do dj dzh times zh dwh, like this. But dj dzh is something I also know, so I can reuse that. And all I have to worry about to do now is dzh dwh, which, as you can see, is just x. Okay, so now, as what we did basically in summary, is we work our way backwards through the graph, and we compute all the gradients we want, step by step. And now that you see how you can do this for 2 layers, you can see how you can do this for any number of layers. If I had a 10-layer network, I would just keep going, right? And if you tried to do that with some crazy 10-layer equation and you didn't know this, it would be impossible. But with this, it's just an algorithmic way to break apart the gradient computations into this organized chain and just attack them systematically. And this is what frameworks like PyTorch and TensorFlow, this is what they do. They're just all the code that does this, essentially. Okay, and they do it efficiently, and that's really all we need. Okay, so how are you guys feeling about this? Is this sort of making sense? Okay, any questions so far on this? All right, let's just talk a little bit about this. We'll finish up here today. It won't be the end of the discussion, but enough for this week. So let's complicate things a little bit. We'll keep all the variables scalar, but let's increase the batch size. So now that means that I have B scalars here. Of course, I still have my scalar weight and bias, but then I have B here, B here, B here, B here. But of course, a single loss or cost at the end. Okay, so the forward pass, I start with these things, and I have to compute all this other stuff. So the equations are here on the right. So we start with xi, this. We compute our hidden scores. We do this for all the elements in the batch. Once those are all done, we can apply the activation function to them, compute our activations again for all elements in the batch, and so on. And finally, we have the little j's specific for every batch element. We sum them up to get the total cost over our mini batch. So we've done the forward pass. We now know all those variables. We've computed them. Now it's time to do the backward pass, where we start at the right side and we go left. Okay, so now the difference between the last slide is we have to keep in mind that we have multiple elements in our batch. So in particular, to start, we're going to do dj dzo I. We're going to do this separately for all the different i's, scalars. And so if I just focus on one I do dj dzo I. Well, that, according to this equation, only one term in the sum, the ith term, will be relevant, so I can drop all the other terms, focus on this, and then do dj dzo I. In order to know what that is, you have to tell me more about j, but for now, we'll just call it j prime. J prime evaluated at zoi. Okay, so now we know that. Next, dj dahi. Okay, so we're looking again at a single term within this mini batch. So here's where we have to ask the question, will this involve multiple paths through here or a single path? Because you can see there are several variables at that node. So if we have a situation where the information we're computing flows through several variables, we have to use the multivariable chain rule. So what do you think? If I'm focusing on a single I, does it flow through several variables here or one variable? Okay, so to figure that out, we can, let's look at, okay, let's think about, let's ask the question, if I have a single AHI, does that involve, does that touch different ZOs? So that is really about this equation, right? So if I have a single AHI, that for a single I, does it affect several output I's? No, just one of them. So even though there are several nodes here, or several variables at that node, when I look at one variable here, it only passes through one of those to get to the output. So I do not have to use the multivariable chain rule. I can use a single variable chain rule. Okay, so basically then it's the same as on the last slide, dj dzoi times dzoi dahi. This one we already computed here. And then this one, this is the ith case here. You can see that derivative dzoi dahi is just w0. Okay, so we're good with that. And then we move on. This dj dzhi, so again, just looking at a specific I, we're going to use this node as the intermediate one. So here again, the question is, if I have a single I here, does this affect all the different I's here or just a single one? Just one, right? So we have to look at this equation. This equation says that a single ZHI only affects a single AHI. So there's no crosstalk across the batch when you go through this activation. So that means when we do this, we can use the single variable chain rule, which takes this form. We already computed this, that's done. So we just need to do DAHI, DZHI. This is the equation. You can see that's just little h prime evaluated at ZHI. Okay, so we're done with that. Now let's think about the parameters. So imagine that I take B0. I want to do DJ DB0. So I'm going to break that up into this. So now I have to ask the question, for B0, how many ZOIs does that information flow through? Does the bias here affect only one of these, or does it affect all of them? All of them, right? And you can see that from this equation. This single bias affects all of them for all the different I. So that means I have several, I have to use the multivariable chain rule here. So I'm going to have a sum over the I's, and then I'm going to have DJ DZOI times DZOI DBO. And these guys, we already computed all of those before. And then this one, DZOI DBO, we can see that that's just one. Okay. So then basically the process is similar. WOs, yes, a single WO does affect all these. You can see that here, it affects all the ones in the batch. So we have to use, again, multivariable chain rule. And so we have a sum here. But otherwise, everything is the same as the last slide. And of course, it's all the same down here. We can choose for DJ DBH, we choose this as our intermediate node, but we see there's several variables there. And yes, each BH does affect all of these batch elements, so we have to use multivariable chain rule. So that's enough for today. We'll move on to the vector case next time. The story gets a little bit more interesting, but I think this is enough. And enjoy the weather this weekend. It's supposed to be nice. See you guys on Monday.